You'll recall from your pre-read on natural capitalism that in the first industrial revolution, people were relatively scarce, but nature was abundant. So it made sense to use people more productively to exploit seemingly boundless nature. Yet in today's next industrial revolution, people are abundant and nature is scarce. So we must instead dramatically raise resource productivity. The biggest, most concentrated, yet most varied and challenging place to do that is in industry. Global industry is extremely skillful in saving energy and money, but it can do even better. For example, Dow Chemical set a goal to cut its energy use in half in 20 years, and it superbly captured over $19 billion of energy savings on a $1 billion investment. Yet, even Dow hasn't yet done much of what I'll next show you such firms could do in fluid handling. That means moving water and other liquids with pumps, moving air and other gases with fans and blowers, which have the same physics as pumps, just different fluids and flows, and also using certain compressors. At least half, more likely 3/5 of the world's electricity runs motors. Half the world's motor torque runs pumps and fans, mostly pumps. Pumps move liquid through pipes. IPCC in 2014 said that 43 to 57% of pumping energy in about 32 countries could be saved in principle, and 27 to 49% could be saved cost effectively. So let me explain how that estimate omits its biggest opportunity and why the cost effective potential is actually nearer 90% or more. If that tenfold saving sounds to you incredible, just consider that at this instant, your heart is pumping blood about 10 times as efficiently as typical industrial pumping systems move water or other liquids. More on that later. More than any other common electricity using device, except resistance heaters and incandescent lamps, which are 95% electric heaters that convert the other 5% of their energy to light, big electric motors have a huge ratio of operating cost to capital cost. Something like 97% of their life cycle cost is energy. A typical industrial motor running constantly uses its capital cost worth of electricity every few weeks. But few managers notice because electricity is invisible. The electric bill has no line item for motors, let alone that particular motor. And anyway, the aggregated bill is sent to some faraway accountant to pay. To make that cost visible, try installing on a few big motors where the manager will see them while walking around, a taximeter-like device displaying in dollars the cash flow invisibly pouring through each motor. That gets attention. There's a lot to be done. RMI found in 1989, and the shareholder-owned utilities think tank, the Electric Power Research Institute, agreed a year later, that roughly half of typical industrial motor system energy could be saved by retrofits paying back in about 16 months at a 5 cent a kilowatt hour tariff. Excuse me. It would be cheaper today. But before we examine how to do that in, say, a pumping system, let's try to minimize flow and friction first, so we need less pumping and hence less drive power. That is, one of the most important insights into doing the right things in the right order is so obvious that with one small Australian exception, I haven't yet found an engineering textbook that mentions it. Start at the end or start downstream. We already saw this with buildings and automobiles, but perhaps it's most striking in factories. For example, from the fuel burned at the power plant to the end use, many successive losses compound. So in a typical industrial pumping system, only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left, and they turn into compounding savings. Every unit of flow or friction you save in the pipe saves 10 units of fossil fuel cost, emissions, and what Amory Lovins calls global weirding back at the power plant. And as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. If you didn't see this diagram, you might suppose that since the energy saved by a chain of successive actions multiplies, because each successive saving leaves left to be saved by subsequent actions, And multiplication is a transitive mathematical operation. It doesn't matter in what order you do those steps, and they're all equally important. I hope this diagram will help you remember that engineering is not the same as arithmetic. Starting downstream with the delivered service leverages enormous savings further upstream in energy and sizing and capital cost. So always start your savings downstream. So starting at the end, really the end is off the right-hand side of this graphic. It's about why you want flow, because less or no flow needs less or no pumping. Buildings that stay cooler, buildings that keep you feeling cool passively, more efficient equipment that needs less cooling will need less pumping or none. Another way to eliminate pumping is to let gravity be your friend. The architect Maya Lin, who designed the Vietnam War Memorial, did the conceptual design for a factory in the Bronx to recycle office paper from Manhattan. And land was costly, so she stood the plant up on end, pumping water up once, and then everything would run downhill. The industry experts thought she was nuts and then realized she had a good idea. I once met a Canadian mining engineer who was sent to an old mine that over decades had kept raising the dams around its growing tailings ponds, pumping ever more water through more complex piping that developed hydraulic problems like water hammer. The more he looked, the more puzzled he became. One way he figured out what was happening and went in and told his colleagues, hey guys, we're pumping water downhill. And they were, but they didn't seem interested. So he went back up, opened the valves, turned off the pumps, and felt better immediately. I once visited an ice cream plant with best-in-class equipment, but the insulated box containing pipes to freeze the cream also contained the motors, compressors, and pumps all releasing heat. So they had to work harder to cool. You don't have to be an engineer to see what's wrong with that picture. First, minimize the load, and especially minimize the reasons for the load. Next, and omitted by nearly all practitioners for about the past century, we can deliver the minimum required flow with 80 to 90% less friction by properly designing the piping system. If pipes are made not skinny, long, and crooked, but fat, short, and straight, friction drops by 80 to 90%. If this were done worldwide, such proper pipe and duct design could save roughly a fifth of the world's electricity, or half the world's coal-fired electricity, with extremely juicy returns. The typically observed paybacks are under a year in retrofits and less than zero negative in new builds. But this opportunity remains largely unnoticed and unpracticed. It's in no official study, industry forecast, climate model, or standard engineering textbook. Why? Because it's not a technology, it's a design method, forgotten since the Victorian era, and most people don't yet think of design as a scaling vector, a way to make things big fast. Stanford lecturer and treasured colleague Peter Rumsey estimates that about 15% of US electricity, I suspect maybe even more, goes to overcome friction, most of which can be designed out. This is so important, I'm going to devote the next dozen slides to it. The physics is obvious, but the logic is ignored in practically every building and factory in the world. For example, normally a critical pump with an in-place spare pump would be laid out like this, so the flow always go through two right-angle bends. That means friction. Why not lay it out like this, so the main flow has no bends and also fewer valves? The same logic applies with identical pumps in tandem, a very common arrangement. At California's Oakland Museum, Peter Rumsey retrofitted an efficient layout into the condenser water pumping loop. And that cut the pumping energy by 3/4 with a 2 or 3 month payback, and it eliminated 15 pumps that will never again waste energy and maintenance costs. I love mega pumps. And notice in the upper left, the Y joint, the sweet bend running then diagonally through the air, the fat pipes, small pumps. And when Peter also repiped the museum's chilled water loop and added variable frequency drives, VFDs, which are also called adjustable speed drives or ASDs, he doubled the flow and saved 85% of the energy. Now, to help the pipe fitters understand how to minimize friction, he simply asked them to lay out the supply pipes as if they were drains, because in another part of their brain, they know that drain pipes, whose flow is driven only by gravity, not pumps, will clog if they're too small or if they have many elbows and joints, especially, those right angle bends. Similarly, here's how most big buildings pipe cooling tower water back to the condenser. But if we lay it out instead the way Peter does, everything gets better. Less space, weight, noise, friction, energy, fewer parts, smaller pumps and motors, less installation labor, less maintenance, higher uptime. The only obstacle is force of habit. Bend minds, not pipes. How do we do this magic? We make two changes in the design process, the design mentality. First, we specify big pipes and small pumps, not small pipes and big pumps. Friction in a pipe falls as nearly the fifth power of its diameter. So how fat should the pipe be to optimize the friction? The textbooks say to make the pipe just as fat as will repay its extra cost over the years from the saved pumping energy. Sounds plausible, but it's wrong because it leaves out the capital cost of the pumping equipment. That's the same error as sizing insulation only for saved heating energy, not also for the capital cost of the heating equipment that my house eliminated. Now, a pumping system's pump and motor and inverters and electricals all have to be big enough to overcome the friction in the pipe. So their size and roughly their capital cost will fall as nearly the fifth power of pipe diameter. Yet the capital cost of the fatter pipe rises as only about the second power of diameter. So when we optimize the pipe as a component, we're pessimizing the system. Instead, optimizing the whole system at once yields fat pipes and tiny pumping equipment, so the total capital cost goes down. Okay, so far? Now, the second shift in logic is even simpler, therefore harder. We lay out the pipes first, then the equipment they connect, not the reverse. The logic is simple. Friction inside the equipment doesn't depend on where the equipment is, but friction in pipes between the equipment matters. It depends a lot on where it is. So the geometry that optimizes different devices' locations can minimize friction. Traditionally, we put the tanks, boilers, and so on in some convenient, arbitrary, traditional place, and then we call in the pipe fitter and say, please come connect point A to point B. But by then, A and B are rather far apart. Other stuff got in the way between them. They're at the wrong height. They face the wrong way. By the time the pipe snakes across the space, all dressed in neat right angles like they teach us in trade school, it has about 3 to 6 times the friction that it would have had with a straight shot. So we should design out friction by using fat, short, straight pipes rather than thin, long, crooked pipes. And if your retrofit also cuts flow through the same pipe, this effectively oversizes the pipe, cutting friction as nearly the fifth power diameter, and energy use will fall as roughly friction times the cube of flow. In a Dutch industrial case, this approach cut the pumping energy by at least 7-fold. Actually, the engineer told me he ultimately measured it at 12-fold with lower capital cost. As a free bonus, it also saved 70 kilowatts of heat loss with a 2-month payback because it was easier to insulate short straight pipes than long crooked pipes. But belatedly, I realized that we had left out 8 additional benefits we could have captured, each justifying even bigger savings. The system's more compact, it weighs less, it's quieter. Those all have a value. It has a wonderfully clean layout for easy maintenance access, reducing maintenance cost, but it'll need less maintenance anyway because there's less stuff to go wrong, so uptime will improve. The pipes will last longer without so many elbows being eroded by liquid turning the corner. And there's more flexibility for later debottlenecking if desired. I later estimated that had we properly counted and valued those extra benefits, we would have saved not 86 to 92% of the pumping energy, but probably nearer 98% with even lower capital cost. Indeed, in adding some piping in my own house, as you saw in the virtual tour, we saved about 97% of the friction and pumping power. Now, a decade ago, I had a PhD engineer review all the main US engineering textbooks, and none correctly presented 2 design cases that are pretty basic. They say to optimize pipe diameter against saved friction, ignoring the capital cost of the pumping equipment, and to optimize thermal insulation against saved heat loss, ignoring the capital cost of the heating equipment. In other words, they said to optimize the wall or window rather than the house. Nearly all $10 trillion worth of US houses were designed by that piecemeal method. But notice this is the opposite of the usual methodological error. Many businesses ignore life cycle costing by counting only capital cost, not operating cost. But oddly, in optimizing components against the system containing them, the designer tends to count only the operating cost, not the capital cost, beyond that of one narrowly defined component, the insulation or the pipe. Well, we want to make neither mistake. Optimal piping can look strange. Engineers used to seeing big, powerful pumps as on the left tend to get nervous when they see teensy little pumps as on the right, but they can't quarrel with the design calcs or the measurements. I'm actually currently writing a how-to manual for the chief engineers of China's top 17,000 factories. It's called the Dao of Pipes, Guangdao Jidao, Huafang Weijian. It's a hilarious dialogue between two fictitious Chinese factory engineers discovering together how to untangle their pipe noodles. Let me show you a few more of the nice photos that they discuss, kindly supplied by Peter Rumsey and by his and my mentor, Li Englok. In the Singapore biotech plant, in the lower left photo, the lower gray pipes feeding up into the manifold are slanted to match the direction of flow, like merging into traffic. The pump in the other three photos is raised up on a plinth to meet the pipe, rather than bending the pipe down to the floor-mounted pump and then back up again. The big pipes are even stacked vertically to save floor space, because Singapore has very high land prices. Don't normally see that. Neat right angles called orthogonal pipe layout look pretty and orderly, and strangely, many codes and specs actually require them. Such layout became habitual because it was easy to draw. Well, nowadays, the computer does the drawing. Design software should allow and even encourage non-orthogonal layout, diagonals and curves to save energy and money, because in pipe layout, ugly is beautiful. See how the cooling tower piping on the left is elegantly slanted to ease the flow. At the upper right, the green pipes and blue pumps were added to older equipment. The pumps are oriented diagonally where they need to go, not at the customary right angles. The computer drawings below that photo show how three chillers, the tan things that are not visible in the photo above, were not aligned in a neat row, but were staggered just the right amount so diagonal pipes on both ends could minimize bends. If there were more room, the chillers could even splay out at different angles, each straightening the piping a bit more. Sometimes equipment could even be advantageously tipped out of its normal vertical orientation if its design allows. Of course, very few designers think this way. More often, we see these kinds of pipe noodles all crammed together as if the installers were paid by the elbow, which I guess they more or less are. In the brewery at the upper right, I found the red traced pipe starting at the upper left could have had 11 fewer elbows if the installer had rotated the tank at the upper left by 30 degrees around its vertical axis before plumbing it, and then run a diagonal straight to the destination. Looking at the chillers at the lower left, just imagine how many fewer elbows there would be if the chillers and their headers were at about the same vertical level. Now look again at that image on the one to the right of it, with the aqua and blue pipes. If the big sort of purple pipe running across the ends of the chillers were rotated a bit around its axis, all but the lowest of the elbows between it and the chillers would vanish. Probably the dark green pipes of the lower left could be straightened out too. I think the record holder for untangling pipe noodles may be a brilliant Stone and Webster engineer I met who fixed the layout of the front end of an ethylene plant to cut the number of elbows from 29 to 3. These were stainless steel elbows, almost a half meter in diameter, therefore extremely expensive. We agreed that the next batch of engineering recruits to his firm would be taken to the main lobby, which had great big physical models of plants the firm had designed. And my friend would take apart one of the models, pocket most of the elbows, and tell the recruits to figure out how to untangle the layout and put it back together. Good idea. Here are a couple of further winners from Singapore. Wow. Whoever designed that was thinking about something else. So how would you improve these layouts? The one on the left is kind of interesting. If you kind of rotated those green manifolds a bit, maybe you could run very short diagonals to pumps that are raised up with a catwalk to get to them for maintenance, instead of having all those joints going down and up again. Save a lot of plumbing expense. There's some other stuff you could do there too, although you notice they're pretty good about the long purple connection not having right angle bends. On the other hand, maybe it could run in an arc. The one on the right, that has some pretty interesting possibilities, which I'll leave as an exercise for you. One of the world's best pipe untanglers, Peter Rumsey, notes that when he lays out pipes properly, often at lower cost, he's commonly asked to justify why it doesn't look like normal or traditional layouts. And by the time he educates the client, it's harder to keep up with the project schedule. He doesn't get paid for that extra educational work, so his profit margin shrinks or vanishes. Ideally, he can work only for clients who already understand the issue or who trust him to get it right, or both, and help those clients outcompete their rivals and kill off all the ancient ignorances that way. But this does take longer, takes patience. I mentioned the typical industrial piping is so overfitted that it has about 3 to 6 times the friction it should. But that's partly because the fitters may not be selecting low friction pipes or fittings. The surface finish matters, and the old design guides specification tables may not take that into account. Sharp bends can have double the friction of gradual, so-called sweep bends. Segmented bends, where they bend a piece at a time, can have again as much friction as continuous smooth bends. 90-degree elbows have a huge amount of friction, and you can look at loss coefficients that show that anything that disturbs the flow is introducing friction, probably about the worst being a globe valve. Now, some valves are necessary, for example, to isolate sections of piping for repair or for emergency shutoff, but we shouldn't use valves to reduce and adjust flow. We should let the electronic motor drives do that by changing the pump speed and hence the flow. Lots of valves are unnecessary. Balancing valves are typically a sign of excessive pipe friction. You know, you wouldn't use balancing rheostats in your home wiring to even out the current flows. You just make the wire fat enough and let Mr. Kirchhoff do the work. If there's too much friction in one place, reduce it. Whereas actually the approved ASHRAE method for duct balancing is to balance it by adding more friction in places that don't have enough. Huh? What are they thinking of? And then choice of valves matters a lot. Where you really need them, some simple choices can greatly reduce friction. For a lot of uses, I like full port ball valves, which have essentially no friction when wide open. It's just like a straight pipe. But gate valves have significant friction, and globe valves are awful in their friction. And yet they cost more than the ball valves. And I'm not even counting capital credit for shrinking the pumps and motors and so on. Ball valves do give good control, but adjustable speed drives are even better. They give exact control, and we shouldn't throttle the flow at all. And then there are these things called three-way valves that are generally worth taking out. Okay, now that we've minimized flow and friction, it's time to go further upstream and optimize the pump. But first, let me insert a remark about the buildings lectures example of purely radiant cooling in Singapore. It's a remark I couldn't make back then because you hadn't yet seen this diagram. Most people who are asked to save Singapore air conditioning energy will start by seeking a better air conditioner. That's like seeking a more efficient pump. It's worthwhile, but only after you have captured the higher leverage savings further downstream and shrunk or eliminated the air conditioner. So for thermal comfort, start with how much you need and how it's delivered. Choosing radiant rather than air delivery of cooling is analogous to choosing low friction piping. In the same way, radiant cooling needing much less temperature difference makes the cool water supply system much smaller, simpler, and more efficient. Of course, starting even further downstream by expanding the conditions in which people feel comfortable, for example, because of air movement, leverages even more upstream savings, just like reducing the amount of flow needed from a pumping system. So in delivering flow or comfort or any other service, start at the end. Okay, now let's return to our flow system and to its third step, optimizing the pump. Pump optimization is a common subject of industry seminars. Engineers learn about it all the time. If you don't specify the efficiency and preferably the exact model, you're likely to get whatever pump the supplier happens to have in stock, maybe because nobody else bought it, or the one that's easiest to get, or the one that comes from a firm that maintains the warmest relationship with the supplier. In some countries, that means bribes. Peter Rumsey not only finds that properly specifying efficiency can yield over 20 percentage points. Let me try that again. Peter Rumsey says that not properly specifying efficiency can yield upwards of 20 percentage points worse efficiency than it should be. So you have to pay attention to speccing it right. He requires pumps with the design efficiency at least 75%. Otherwise, the supplier may ship something in the 50s. Similarly for fans. If you shop carefully, far more efficient pumps and fans often don't actually cost more. But even if they did, it would usually be worthwhile. Also, you do need to specify the pressure head and the flow actually experienced by the pump once you've installed it, not just some rule of thumb. Most pumps are oversized by misapplying many successive design margins. Moreover, even a great pump will perform miserably if it is run far from its optimal design point, the so-called bullseye on the efficiency map. So you need to spec it right, adjust its actual operation initially, and then correct it later to seek optimal conditions, maybe as things settle in and wear and some of the variables shift a bit. It's also wise to give yourself more margin by preferring pumps and fans that have a big bullseye, so they're not so sensitive to exactly how well you are matching their optimal conditions. Or as Mr. Lee says, in this analogous case of a fan, this fairly efficient 85% Vade axial fan is like a Formula One driver. It won't win the race without Schumacher driving it. Errors in its application or installation or operation could easily lose tens of percentage points in practice. Like the US Navy chillers that when we measure them on a ship were among the worst we'd ever seen, even though they'd been superlative in the lab. The difference was that they were installed in the ship with very cramped pipes and ducts set for suboptimal operating conditions, not properly controlled, so they couldn't perform it anywhere near the potential that they had correctly exhibited in the lab. Fluid handling machines lose efficiency rapidly at part load. This typical chilled water system for cooling a big building runs at a total power of 1.5 kilowatts per refrigerative ton of cooling at 50% load. Even better at full load, that is towards the right, but off the chart awful further to the left at a third or a quarter of full load. It's just terrible. The pumps can easily lose half or more of their full load efficiency when they're running at low load. Conversely, as we saw in Buildings Lecture 2C, a really optimized chilled water system can more cheaply achieve 0.44 whole system kilowatts per ton at the design hour in Singapore. In other words, less than a fifth of the 2.43 kilowatts per ton shown here at half load. And I just see that I misspoke. I referred to the 1.5 kilowatts per ton at a typical chilled water system. It's not the system, it's the chiller plant. So you have to make sure you're adding up everything. Now, if the load varies widely, you should spec pumps with a big bullseye or optimize them with ASDs. adjustable speed drives, which help compensate for prevalent oversizing even at constant flow, so you can trim them back to just the right speed. Or consider multiple pumps, often of different sizes, what's called multiplex unequal. Each pump is optimized for a particular piece of the load curve, so you can operate that when you need it. And of course, the ASD eliminates the old throttling valve, the stupid way that much flow is still controlled. A motor without an ASD is like an internal combustion engine car without a transmission. It'll work well in a narrow speed range, but it'll struggle or stall at other speeds. But a pumping system with a throttling valve is like driving with the accelerator always floored and controlling speed with the brake. Actually, it's worse than that because the pump's power varies as the cube of its flow. And of course, technologies keep improving. A generation ago, a great fan for distributing lots of air in a big building, like the one I showed 2 slides ago, might be at best 85% efficient and come with a motor with an efficiency rating called IE3. Now it can get 92% efficient with a big bullseye on the right at very high efficiency, and it can come with a variable speed IE5 motor, better. That's in this case 93.1% efficient, and better motors still to come. More on motors later. But you have to apply the fan properly. In this application example, a Xerax vane axial fan can be 92.1% efficient if it's run at exactly the right conditions, although it's 90%. Bullseye is actually quite a large zone. Moreover, up to 1/4 of the fan energy can be saved by using a carefully designed diffuser to regenerate dynamic pressure into static pressure that can then overcome duct friction, which of course you should first minimize with the duct equivalent of fat, short, straight pipes. So this dynamic pressure recovery applies Bernoulli's principle that the total pressure of a fluid is constant, but you can vary its proportions of static and dynamic pressure by uniformly changing its velocity. If that went over your head, don't worry about it. That's a mechanical engineer's point. Just be sure that you're comparing like with like. So a 92% efficient Novenco Xerax fan might mean 85% efficiency once you include the losses in the motor and the inverter. It's the power electronics that drives the motor. All these components do keep improving. Electric race cars motors can be 97, 98% efficient. Their inverters 98 or 99% efficient. So if we use those in this case with the fan, we'd raise its system efficiency to 87 to 89%. Next generation inverters will progress from yesterday's silicon and today's silicon carbide switches to tomorrow's just coming on the market gallium nitride or GaN, G-A-N switches, which are so efficient that the inverter typically needs no cooling. Oh, and by the way, axial fan motors and sometimes their inverters are often sited in the airstream you're moving, often supplying cooled air to cool a building. So downstream efficiency not only saves drive power, but can also avoid rewarming the air that you just cooled. Now, everything you're hearing about pipes and pumps applies also to fans and ducts. The physical principles are the same, only the details and the names differ. Actually, duct friction is even more sensitive to diameter of the duct than is pipe friction. And then there's a corrugated bendable form of duct called a flex duct that can quadruple its friction if it's installed, say, with 30% compression rather than fully extended to reduce the bumps. A pumping system's throttling valve is like a damper to block part or all of the airflow in a duct. Both are equally stupid. And in the graphed example, if you drop from 100% to 20% flow, going from right to left, the damper control, which is the top curve for the airflow, cuts the fan power from 120 nominal units to 70. But taking out the damper and using ASD control, the bottom dark curve, goes from 104 fan power units down to 5. So same flow, smarter method, 93% less energy. Don't get in the way of the moving air, just don't move it as fast. Even good equipment is often installed poorly. Endemic oversizing is often claimed to be needed for flexibility, but just spec the right size now and then design for flexibility. Put in a pad and piping so you can fit a bigger pump if you later need it. But if you don't need it yet, maybe you don't put it in yet. Pumps and pipes are often crammed into tight spaces, as in these photos on the left, or laid out as if they were. So the constrained so-called entering and leaving conditions, pipe bends and fittings that are too close into the pump, cause major turbulence, killing the pump's efficiency and often causing impellers or seals to fail early. So smooth, straight flow and efficient operation require at least 5 diameters of clear pipe run on the inlet side, 8 is ideal, and at least 3 on the outlet side, 5 is ideal. The pipe be as big as the pump connection. If you need to neck down a pipe size, do it far from the pump so the turbulence can dissipate before it gets into the pumps. These are just basic good practice principles, but often ignored. Unnecessary fittings, especially if they're near the pump, also add friction and turbulence, such as the ubiquitous end suction diffuser. It's an undesirable elbow and fitting size reducer combined with straightening vanes to reduce swirl caused mainly by pipes that are too short or crooked coming into the pump. On the discharge size, these triple duty valves, check and throttling and shutoff valves, are another artifact that seems to save capital costs, but actually needs more energy and bigger pumps, costing more than if you use best layout practice. Just pipe properly and design those things out. Duct systems can present the same graphic and disturbing images of dreadful layouts with high friction and thus unnecessarily big, costly, noisy, inefficient fans and blowers. Physicist Dr. Alison Bales collected these gems, and somebody commented, "I would use one of those ducts to strangle the designer than the installer." Such details matter and they scale. Peter Greenberg just told me a little story I'll share here because it involves plumbing, not ducts, but same idea. A giant government data center used 100 old humidifiers from the world's biggest maker to suppress static electricity that could damage the chips. But then each unit turned out to be drawing makeup water 92% of the time, and it was supposed to be 25% of the time. What was going on? Well, the float valve wasn't floating. Why not? Because the float was hollow. So in boiling water, as its maker had warned the valve maker in vain, the float overpressurized and then it leaked. And then the continuously flowing makeup water did not efficiently use the 9 kilowatt heater. So they swapped out 100 solid floats for the leaky hollow ones at a cost of $4 each. That saved over 8 million liters a year and 6 gigawatt hours a year. That's well under a 1 day payback. But nobody had previously noticed. Of course, the dehumidifier should have been super efficient ultrasonic ones, but first things first, let's get the floats right. Well, returning to pumping systems, it's often worth repiping, but even if you don't do that, at least the valves can be eliminated or replaced. The pumps and motors can be reoptimized. And even if flow doesn't vary much, and remember, power varies as the cube of flow, you may want real-time digital speed and flow control anyway, just to improve control of the production process. Now, these changes will also tend to improve reliability, and that can also free up maintenance budget and time to leverage savings elsewhere in the plant. So your system boundary needs to keep expanding from the pumping system to the whole process, to the whole factory, to the whole company and beyond. Once you've minimized required flow, pipe friction, throttling losses, which should be zero because you run the pump at variable speed, and pump losses, your much smaller and more efficient pump will probably need a much smaller motor and control, usually an ASD, to provide the needed torque to run the pump. So now let me summarize very briefly our encyclopedic, yay thick 1989 analysis called The State of the Art Drive Power. In the 34 years since then, I suspect the potential savings probably got bigger and cheaper by at least as much as they were used up, and probably more, but we don't really know that, and we should find out. In the state-of-the-art drive power, we examined all significant motor types, the dominant induction type, which most countries call asynchronous, in red, synchronous motors in yellow, direct current motors in green. And our system boundary was from the electric meter to the input shaft of the driven machine. So we counted the efficiency upstream in the wires and controls, in the motor itself, and in transmitting the mechanical torque downstream to the pump or whatever you're driving, but not in it. And we analyzed 12 main categories of successive savings for induction motors, plus those more simply analyzed for synchronous and direct current motors. And together we found these improvements can cumulatively save nearly half the total US drive power energy in 1986, as shown in blue, with paybacks typically under a year, even if electricity were as cheap as 5 cents a kilowatt hour. Industrial electricity is now up around 8-ish. And this 1989 RMI finding is twice what the International Energy Agency most recently found was the profitable potential. And it costs much less than IEA found. Let's see why that might be. First, we're often starting with a really juicy opportunity. Most motors in existing factories are unimpressive. An illustration of typical field findings, in this case for a third of the motors in a chip fab, typical of many kinds of factories a quarter century ago and even common today, found the nameplate ratings on the motors shown as red X's, where the white dots were all the motors on the market in 1996. Those above the dotted line are more or less at the now obsolete efficiency level called IE2. IE1 models were already no longer allowed to be sold, but you can see that's mostly what they had or worse. So this shows 2.5 megawatts of observed motors that could have saved $1.4 million net present value if replaced. Sorry, that's not net, it's just gross present value. If replaced by the best motors then available. And of course, today you'd replace with IE5 or better motors and save even more. The gap between average installed and best sold motors may not even have shrunk yet in many industries, because the motor stock may not be improving nearly as fast as the best new models are improving. Many factory managers inattentively run every motor till it breaks, it fails, even if it is grossly inefficient. They have other stuff to worry about. Well, conventional analyses like IEA's typically assume a package of just 2 drive system improvements, switching to more efficient, but often far from most efficient motors when replacement is needed or scheduled, but not sooner, and adding ASDs, adjustable speed drives, where suitable, which it usually is. Now, those improvements typically save about 15 or 20% of drive system energy and pay back in a few years, but they spread slowly, at most at the rate of routine motor failures, but usually slower because many failed motors are repaired rather than replaced, usually multiple times. 5 or 6 is not unusual. The value of more efficient motors is high. Each percentage point gain to a motor that runs continuously in a typical American industry is worth about $100 per kilowatt of motor capacity. So how many percentage points to be multiplied that way can we save by using better motors? Well, that saving keeps rising. Most old motors, especially those with no or illegible nameplates, are standard efficiency, IE1 or worse. That's the lowest gray curve at the upper left graph. Current standards are at least the top solid line, achieved by the features shown on the lower left in a design transition illustrated at the lower right. Minimal good practice is the top dashed line at the upper left. The International Electrotechnical Commission, or IEC, standard called IE4, or super premium efficiency. IEC standards are observed in most of the industrialized world except the United States, which uses laxer NEMA standard, National Electrical Manufacturers Association. Now, the European Union requires at least IE4 for 75 to 200 kilowatt motors that are very common in industry, starting July 1st, 2023. Until then, 3/4 of a kilowatt to 1,000 kilowatts can be IE3. The US is stuck around IE2 for the moment, but all those old standards are becoming obsolete and words inadequate. Let's do it by the numbers. Some vendors already offer IE5. It's a bit better, especially at small sizes. You see in the upper right graph, and you see some up around the Japanese equivalent to IE6, 7, and 8, which do not actually exist yet as IEC standards. IE6 to 9 are emerging, as we'll see in a minute. And in 2017, an IE8 rare earth-free synchronous reluctance motor from SRAMtechnology.com was advertised, 95.86% efficient at 2.2 kilowatts. At the other end of scale, a giant ABB synchronous motor, 44 megawatts, achieved 99.05% efficiency. Now, looking at these charts, you might think, well, so what? Gaining just 4 percentage points, say going from 92 to 96%, isn't so important. Think about it inside out. 100% minus the efficiency is the losses, which make heat the biggest enemy of motors. So going from 92 to 96% efficiency cuts the losses, hence the heating, in half, from 8% to 4% of the input energy. And that can make the difference between active and passive cooling. And it makes a huge difference to reliability, which is often even more important to a factory's economics than efficiency is. Of course, the two go together. So what does greater motor efficiency cost? Well, maybe zero or less. Among induction motors, nearly all those now in industrial use, more efficient motors generally use more and better copper and iron, so they should cost more to make. But for whatever reason, they're not priced that way. When we last requeried the Department of Energy's free MotorMaster Plus database in 2011, 2 generations of standards had already knocked the worst motors off the US market. So the modelers didn't want to bother requerying their model, but they did so anyway just to humor us. And they were surprised to find there was still no correlation between efficiency and price for common motor types up to at least 300 horsepower, 220 kilowatts. So as shown in the right-hand graph, around 1998, you could buy the most efficient 100 horsepower induction motor cheaper than nearly the least efficient one with otherwise comparable specs, and thus you could save a present value above $20,000 per motor. By the way, efficiency has also been found uncorrelated with price for common industrial pumps, most rooftop chillers, refrigerators, televisions, and a lot of other stuff. So don't assume that efficient equipment costs more. Shop around. Remember, in God we trust, all others bring data. Now, the 2011 version of that comparison for a 250 horsepower motor is on the upper right, and the same conclusion holds. The highest efficiency motor can be the cheapest to buy. I don't know why, but I'll take it. Now, induction motors are the dominant industrial workhorses, but there are other kinds of motors, notably permanent magnet motors, which often use rare earth magnets, but don't have to, and switched reluctance motors, which have no magnets or rotor windings. They're often misunderstood. They're less common, but they offer twice the power density of induction motors, big advantages in ruggedness and flexibility, very diverse shapes, form factors, lower cost. and their often noted torque ripple and acoustic noise are actually artifacts of bad design. They're not inherent features, and they can be made as small as you want by better design and buying a better resolver, which is a sensor for shaft angle. Tesla's Model 3 contains a novel synchronous reluctance and permanent magnet motor to get the best performance and range per dollar. And that shows that basic innovations continue in even the most common and supposedly mature kinds of rotating machines. A little more on progress. In 2014, Hitachi developed a short axial flux 11 kilowatt motor whose amorphous iron core, kind of glassy iron, cut the iron losses by 90%. And then cheap ferrite magnets instead of rare earth magnets could get the same torque out of 1/3 the field strength. The 30% lower losses eliminated the cooling fan, saving more energy and downtime. And the ferrite magnets are very much cheaper than the rare earth magnets used in commercial ABB and Brazilian and Danish motors. And by 2017, a rare earth magnet motor equivalent to a conceptual IE7 standard, 2 notches above the top actual standard, had been demonstrated. You see that at the upper right. And like Hitachi's, that motor has such small losses, that is, it generates so little heat that it doesn't need cooling. In 2021, IE6 entered the market. Next will come IE7. Soon they'll get cheaper with the emerging iron nitride supermagnets, cheaper than rare earth magnets, and potentially more powerful, but containing no rare earths. And of course, progress continues. There's a little Swiss firm, apparently Russian emigres, and their design team now offers small motors up to IE9, which doesn't officially exist yet. Their website mentions compressed magnets, so they don't risk flying apart so much at high speed. And they seem to have expertise in advanced composites for containment. Their website mentions a bunch of other interesting things. And then there's the big Brazilian firm, WEG, that mentions a developmental IE9 industrial motor of unstated size in 2022. GreenTechMotors.com claims a Boeing and NASA-derived lightweight 20 horsepower motor at 97.7%, pretty good. Maybe not as good as this Polnikov. Infinitum Electric's liquid-cooled air core motor substitutes a printed circuit stator disc for iron. So it saves about half the weight and 2/3 of the copper, albeit at lower efficiency than Polnikov, but maybe lower cost. And at this rate, IE10 can't be far off. There's just a lot of innovation going on. And it's a good thing the IEC rates efficiency by numbers, not words, because IE4 is already called super premium efficiency. I think 5 attracts a word like ultra, but you run out of superlatives pretty fast. Well, then again, only the EU and Switzerland and UK have adopted IE4 as the standard for most industrial motors. The IEC hasn't declared any higher standards. China's standard for motors above 3/4 of a kilowatt were raised to IE3 only in 2021. India's voluntary standard for all motors remains IE2. Many older motors are much worse than IE2 or even IE1. So for most of the world's motors, there's a long way to go to get into these rarefied efficiency ranges. Another interesting kind, axial flux motors or pancake motors, are typically over 96% efficient, some 98, 99. They're 5 to 8-fold shorter and 2 to 5-fold lighter, sometimes more than that, than traditional radial flux designs as sort of sausage-shaped motors. And yet axial flux motors have high power and torque, so they're well suited to hub motors for vehicles, but they're harder to design, harder to build. Most novel motors in the 10 to 20 kilowatt per kilogram range of power density are variants of axial flux, like the Oxford Yassa motor on the right. That firm was just bought by Mercedes-Benz. Some handmade electric race car motors are in the 98 to 99% efficiency range. or a point less if you include their inverter. Tesla's new motors are reportedly about 96, 97% efficient. Inverters peaked at 99, but those numbers all keep improving, disproportionately extending range of the vehicle. And the best really big 22 megawatt marine permanent magnet motors are said to get 98.7%, getting right up there toward almost no loss. In 2022, the Brazilian global motor maker, spelled WEG, compared two 220 kilowatt motors at 3,600 RPM. An induction motor, standard workhorse kind, weighed about 1.5 metric tons, and an axial flux motor weighed 51 kilograms. It was 29 times lighter and hence 29 times less materials intensive. Think about that, lest you think about, say, copper shortages. And this starts to explain why the Denso Honeywell aviation motor is now claiming 25 kilowatts per kilogram. That's about 10 times the power density of typical motors in good electric vehicles. But asking which efficient motor to buy misses the bigger picture, because that standard two-measure retrofit, replacing IEC2 motors and adding ASDs, captures only about half the savings available from a whole system approach to the drive system alone, without improving the pumps and pipes or the fans and ducts or other downstream equipment. In other words, our whole system approach doubles the savings and cuts the cost per saved kilowatt hour by about fivefold by sequencing not just 2, but 35 kinds of improvements, thus tunneling through the cost barrier. And this takes no credit for side benefits that are generally worth more than the energy savings. Moreover, this bigger, cheaper saving doesn't have to wait for routine motor burnout, but can often be profitable to do immediately, increasing its present value. Normal practice, of course, is to wait till the motor fails on the assumption that efficiency gains that might justify the efficient replacement's marginal or extra cost would not normally justify its assumed total cost, although actually we're going to buy it anyway later, so it's really a discounting question. But this view counts just one benefit, direct electrical savings based on the higher nameplate efficiency of the new motor measured at its full rated load. It ignores 17 other benefits. What are those extra benefits? Well, first, few motors actually run at or near their full rated load, and that part loading can greatly reduce their efficiency. For example, in a 7.5 kilowatt or 10 horsepower IE2 or IE3 motor, the highest efficiency is limited to the small or medium-sized bullseye in the upper right of the motor map of torque versus speed at the upper right corner of this slide. So you see that little dark blue zone, that's the bullseye. But this German line of reluctance motors offers high efficiency all the way down to about 20% load running at any speed. The gold zone in the lower left graph shows the energy savable at part load by running the 7.5 kilowatt model rather than a normal IE3 motor like the one in the middle map on the right. And the advantage can easily be 10 or 20 percentage points beyond the roughly 5 points you would expect just from going to this IE5 reluctance motor. Now here's a graph showing the same issue over about a 500-fold range of motor size on the horizontal axis on a log scale. As standard efficiency induction motors in red go from 100% to 50% of their 25% of their rated load, that is from solid to dashed to dotted, their efficiency falls off down the vertical axis more or less steeply, especially at the smaller sizes. This is for IE3 in blue, or the old standard IE1 lousy motors in red. So they have a lower efficiency. The IE3s don't fall off as much at part load. That is, the more efficient models have flatter efficiency versus load curves, which is a valuable attribute. But in fact, half of US industrial motors never exceed 60% of their rated load. 1/3 of US industrial motors never exceed 50% of their rated load. So they're running much less efficiently than the full load nameplate rating says. Underloaded induction motors don't just run less efficiently, they also run faster. So they waste more energy in pumps and fans, cube law machines, because they drive more flow than needed, a lot more. And because of these two effects of pervasive oversizing, right-sized new motors will save more energy than expected from comparisons that consider only the nameplate efficiency gain, but not also right sizing. The right-sized new motors will also cost less upfront because although price does not correlate with efficiency, it certainly correlates with size. Rarely upsizing is worthwhile, often to speed processes, but usually right size means one or maybe two frame sizes smaller than the motor that's there now, occasionally three. And the flatter efficiency curve across the load range, hence over the integrated varying loads, also improves flexibility as well as saving energy. Premium motors have higher and flatter power factor too. That's a measure of how much voltage and phase are out of current, causing reactive power loads that you have to pay to generate and transmit, but you can't charge for them. So it hurts the utility and it heats your equipment. So you can reduce distribution losses and capacity needs with better power factor that comes for free as part of the better motor. Premium motors run cooler for lower resistive losses. The cooler the copper, the less the resistance. That also increases the life of the motor because each 10 Celsius degrees of reduced temperature roughly doubles expected life of things that otherwise deteriorate with heat like insulation and lubricant. Longer grease life means less downtime and less frequent lubrication. You start to see a bunch of cascading savings here. So making the new motor the right size saves more energy, saves other costs. And the most efficient new motors also have better bearings. Bearing failures are the cause of 3/4 of mid-sized motor failures. The most efficient new motors automatically correct and they reduce susceptibility to hidden iron damage, which GE found wastes $1 to $3 billion a year of US electricity. And that iron damage is caused by poor rewind practice using the standard so-called stator burnout ovens rather than the TUM method shown on the right and used by the US Navy, where you very gently warm the stator and then persistently gently pull the windings out of the slots with a hydraulic puller. So you end up with a perfectly clean set of laminations ready to rewind the wire into the slots, just as good as new. So just the avoided iron loss plus resizing typically about doubles the savings compared with what you would expect just from rated efficiency. I'm talking here about energy savings. Moreover, the top efficiency motors have less harmonic heating. They better handle phase unbalance and wrong supply voltages. They cut the I²R losses in the distribution wires and equipment. They need less cooling from cube law fans and pumps plus chillers if they're in conditioned space. So you buy the great new motor once and you get 18 benefits. Now, motor efficiency also depends on proper power supply, clean, calibrated, balanced, on precise laser shaft alignment, on avoidance of overhung load, sideways pulls on the shaft that can cut the bearing life at least 5 to 10-fold, especially with, say, fans that are driven by a V-belt that keeps pulling on the shaft. Motor efficiency depends on a white lab coat lubrication culture that dispenses a precise dose of special ultra clean, up-to-date medicine to the bearings, which have Swiss watch-like micro-inch tolerances. fanatically keeping even the tiniest trace of water out of the bearings. And just good housekeeping that keeps the motor clean, dry, cool, and quiet. Not in the sun, not next to a steam pipe, not smothered in dust or in multiple coats of paint so the heat can't escape. Procuring the motor starts with the actual measured load regime, and then it uses MotorMaster Plus software or its foreign equivalent to buy the very best motor for that job. Performance is regularly measured and tracked with barcodes. Rewinds are very rare. They're non-destructive and they're monitored. You don't put the motor back in service until you're sure it didn't get damaged. And everyone has to keep up with progress, reviewing purchasing and lubricants at least annually. A company that still buys motors the way it did 20 years ago is leaving a whole lot of money on the table. Whole system thinking can also capture vital system synergies. For example, suppose you change a fan drive from traditional V-belts like this to a toothed, also called a cogged or synchronous belt. Well, that cuts the belt energy losses from 10 or 15+% to 1 or 2%. It makes the belt last much longer. It eliminates stretch and slip, and so you don't have to go maintain it all the time to retension the belt. There's almost no wear or tension adjustment. And because of those maintenance savings, each saved kilowatt hour costs about -$1. But then you have to use a soft start device or a stretchy flat belt like the Swiss Habesett, because otherwise the inertia of starting up a big centrifugal fan is going to tear the teeth off the cogged belt. Fortunately, most good inverters have a soft start feature. Moreover, if you didn't carefully select your premium efficiency motor, it may run faster than the old inefficient one. That could waste more energy on excess speed and flow than it saves through greater efficiency. So you're going to have to readjust speed by changing the ASD frequency or sprocket size, or in a pump, trimming the impeller. The first of those options is the simplest. You just turn a knob to change the motor speed. So it's simplest, cheapest, easily reversible. Best, of course, would be no belt, direct drive. Even better is no fan or no pump. Best of all is no need to move the fluid in the first place. Start at the end. And don't forget to turn stuff off when you don't need it. Moriseiki company in Japan got so careful about turning off unused functions on machine tools that they saved 40% of the power in routine operation and 80% across all hours, which tells you a lot of stuff was being left on over. Fans and pumps are just the most common of an immense range of shaft-driven equipment. Many chemical and food plants also do a lot of mixing. Here's a little example of a radically simpler mixer developed by some Australians a decade ago. The viscous fluid they're trying to mix runs through a straight pipe with no pressure drop, almost none, but it has slots in the walls surrounded by a concentric rotating pipe. And the result is equal or better mixing with 80 to 96% less energy, or equal or better temperature homogenization with 60 to 80% less energy. Cost and maintenance are lower too. I offer this just as a little example of fresh thinking by bringing beginner's mind to an old and common industrial problem of mixing gooey stuff. But all these smart gadgets are as nothing compared to the design brilliance we find in the greatest design treasure house, nature. So let me end by turning there for bigger and deeper ideas about integrative design. We are all rank amateurs at design. This whole heat, beat, and treat philosophy of industrialism, highly evolved over thousands of years, is primitive compared to the way nature has developed over billions of years. So the other design revolution paralleling integrative design is biomimetic design. Innovation.
Sorry, one more time. Here's what I found.
I don't know where Siri is, but I hope she'll go away. So the other design revolution paralleling integrative design is biomimetic design, innovation inspired by nature. Here's how I described it for Time magazine in 2007. Janine Benyus's luscious 1997 book, Biomimicry, Innovation Inspired by Nature, is unique and profound. In the book, she not only invents a new field that she's named biomimicry, but she inverts the way we all think about design, the alchemy that turns intention into action. Benyus draws her design inspiration from nature's wisdom, not people's cleverness. Some 3.8 billion years of rigorous testing and evolution have exposed the design flaws of roughly 99% of nature's creations, all recalled by the manufacturer. The 1% that have survived can teach powerful lessons about how things should be built if they're to last. For example, nature's design genius has led to the creation of bat-inspired ultrasonic canes for the blind, synthetic sheets that collect water from mist and fog, as desert beetles do, and paint that self-cleans like a lotus leaf. Little plastic film patches have been designed using adhesiveless gecko foot technology with nano hairs adhering by van der Waals forces, so the carpet tiles can be stored in a big roll, but also easily removed by just unpeeling them singly. Equally promising, we'll soon make solar cells like leaves, super tough ceramics that resemble the inner shells of abalone, and underwater glue like mussels use. We'll make bulletproof fibers as spiders make silk, under life-friendly conditions in their bellies from digested flies. We'll make cellulose the way hummingbirds spin sugar and sunlight into nests. Maybe we'll get as smart as forests. Biomimicry isn't biotechnology. Biomimicry learns and emulates how spiders make silk. Biotechnology transplants spiders' silk-making genes into goats, then sorts silk from milk and hopes the genes don't get loose. Biotechnology is smart kids in an oil depot with matches. Biomimicry is wise adults in a rainforest with flashlights. Biotechnology is pure hubris. Biomimicry is luminous humility, treating nature as model and mentor, cherished not as a mind to be stripped of its resources, but as a teacher. Steering this design revolution is a centered, gentle, funny, lovely lady who lives in North America's Montana Rockies, observes deeply, writes with rare beauty, and lectures breathtakingly. By reorganizing the biological literature around function, not organism, to reveal which organism knows how to solve your design problem, Benyus and her colleagues at the Biomimicry Build and Biomimicry Institute in Montana are starting to help the world of the made work like and live harmoniously with the world of the born. This will change your life. It's already changed mine, and it may save the world. Biomimicry reveals how things work, how they're made, and how they fit. An Alabama hairdresser watching TV news reports of otters dying after their fur got soaked in spilled oil wondered if the human hair swept up from his salon floor every night could soak up oil. Yeah, it did. Now mesh bags of recycled hair are stockpiled by firms that remediate oil spills. Lotus sand in the upper right photo is a German paint that keeps buildings clean by using lotus petal design to nucleate water droplets that roll down and strip off the dirt. Particle glue has now been mimicked. IBM self-assembles certain computer screens with a low temperature process akin to how abalones make their super tough shells. So you type your design question into asknature.org and you'll get the names of the organisms that have solved your problem, the scientific literature on how they solved it, and the industrial contacts who are imitating how they solved it. And for gorgeous images and explanations of biomimetic design solutions, remember to download free and inhale frequently the online journal Zygote Quarterly. In San Rafael, California, Pax Scientific's founder, Jay Harmon, an Australian sea captain, has developed a new kind of hydrodynamics, displacing centuries of supposedly mature practice. To declare an interest, I own 0.11% of this R&D company's shares. Jay is a keen observer of shapes in nature, like Darcy Thompson's, and one day he noticed a ropey Fibonacci structure in vortices, like water draining out of a bathtub. Picture at the far left, upper left. So he froze such a whirlpool in acrylic, realized it must be the minimum energy shape for that air-water surface, and then made a brilliant inductive leap that, gee, maybe a rotor with that shape could move fluids with minimum energy. And he did so in these fan and pump designs. So he notes that if you're roughly 100,000 kilometers of fractal blood vessels in your body, down to the tiniest ones, had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But in fact, your third of a kilogram, 1.5 watt heart suffices, because your blood follows nature's standard design, laminar vortex flow. So the rotor, pump rotor at the lower right, now in the Museum of Modern Art in New York, emulates the water vortex at the upper left. Such rotors raise efficiency by about 20 or 30%, not quite violating the pump equation. Early practical applications in fans, pumps, and circulators are starting to enter the market, with dozens more attractive opportunities in other sectors. Notice that in the kind of inside-out version on the right, called a Blade Runner hydroturbine, fish can pass through unharmed and doesn't clog. You get much higher torque and efficiency. There's a nice book called The Shark's Paintbrush all about this stuff. PAX's fans are far more efficient and quiet than conventional ones. The latest at the bottom, look at the lower left, uses 70 to 85% less power per unit of flow than its competitors like Holmes, Vornado, even Dyson. And they provide higher air velocity with far less noise. Some of them might look conventional, but mathematically they're not. They're subtle Fibonacci features in the shape. This growing family of products has many applications that we have barely begun to imagine. And one successful early use that's pretty much swept the market is the big tanks that hold purified municipal water before it's sent out for use. That water has to be kept circulating to keep its chlorine or ozone or other disinfectant active. And that normally needs a giant rotor like the one at the upper left, driven by hundreds of kilowatts. The fist-sized version in the upper center photo with one of our ex-interns who was on the Stanford volleyball team, you might guess, it's driven by a 50-watt motor and outperforms the one, the huge one, by setting up ring vortices in the lower center illustration. They require almost no energy to keep circulating. And you can see it actually happening in the upper right. And now it's taken over this market with thousands in use. The biggest unit uses only 300 watts to keep over 40 megaliters well mixed. That's like a football field flooded over 9 meters deep. It's a lot of water. And since these biomimetic rotors' performance does not depend on scale nor on Reynolds number, there's even more than we thought to be saved in the roughly 30% of global electricity that runs pumps and fans. Modern pumps and fans are marvels of Victorian technology, but nature can do even better if we humbly receive its design lessons. I would encourage you to look around asknature.org's treasure house. Such work is rapidly evolving as smart businesses realize that they'll be disadvantaged if they don't have a biologist at the design table. There are enormously many kinds of industrial development we could have discussed, some widely used, many very specialized, but I think rather than going further down that rabbit hole, we would do better to look at some real case studies of redesigning a whole industrial plant and process, drawn with due discretion from RMI's industrial practice over decades. And that's what our third and final industrial lecture will do next. Thank you.